Numerical 16. Calculate the effective resistance between the points A and B in the network shown below. Let us label resistors first: R1, R2, R3, R4 and R5. And as you can see, R2, R3, R4 are in parallel. So let us first simplify that network. 1 upon R2 plus 1 upon R3 plus 1 upon R4, 1 upon 12 plus 1 upon 6 plus 1 upon 4. LCM, of course, 12. 1 plus 2 plus 3, 3 plus 3, 6 by 12, 1 by 2. So Rp is equal to 2 ohm. So this circuit diagram now can be redrawn like this: 2 ohm, 2 ohm and 5 ohm. So now equivalent resistance between A and B is simple addition of all the resistors because they are connected in series. 2 ohm, 2 ohm plus 5 ohm. 4 plus 5, 9 ohm is the final answer. 17th. Calculate the equivalent resistance between the points A and B in the figure. So between the points A and B, if we start traveling from point A and go to point B, this is, we can say, the junction point. Okay, point A itself is a junction point. From that junction point A, current divides into three parts. So this is your path number 1, this is the second path, and this is path number 3. And at this point, once again, all three currents combine and make the total current of the circuit. So as we already know that if between the 2 points there is a network of resistors, first we identify number of paths. That we already did. How many paths are there? 3 paths. Next, simplify each path. And we know that all resistors connected on a given path are always in series. So for path number 1, for path 1, resistance, equivalent resistance is 3 plus 2, 5 ohm. Path number 2, there is only one resistor on path number 2, so that is already simplified, 30 ohm. And then path number 3 is 6 plus 4, 10 ohm. So now this circuit diagram will look something like this. So on path 1, 5 ohm. On path 2, 30 ohm. On path 3, 10 ohm. And then we can find equivalent resistance. So 1 upon Rp is equal to 1 upon 5 plus 1 upon 30 plus 1 upon 10. So 1 upon Rp is equal to, LCM is 30, 6 plus 1 plus 3, 10 upon 30, 1 by 3. So Rp is equal to 3 ohm, and that is the equivalent resistance of the entire circuit diagram, 3 ohm. Next question. In the network shown in figure, calculate the equivalent resistance between the points A and B and A and C. Alright, so pause the video and try to solve this question first on your own. Remember that between the 2 points, when we want to find out the equivalent resistance, first we identify number of paths and then simplify, and the identified paths are in parallel. Okay, so between A and B, RAB first. So now between A and B, This is path 1. This is path number 2. Alright, so on path 1, all resistors are in series 2 plus 2 plus 2, 6 ohm. And on path 2, there is only one resistor, 2 ohm. Now both the paths are in parallel. So 1 upon Rp is equal to 1 upon R1 plus 1 upon R2. 1 by 6 plus 1 by 2. So 1 upon Rp is equal to 1 plus 3 by 6, 4 by 6. So Rp is equal to 6 by 4, 3 by 2, 1.5 ohm. This is our RAB, equivalent resistance between A and B. Now for sub question B, let me redraw the circuit diagram once again. 2 ohm, 2 ohm, 2 ohm and 2 ohm. This is point A, this is B, this is C and this is D. Now here our aim is to find RAC, equivalent resistance between A and C. So as you can see that there are two paths again to go from A to C. Okay, this is path number 1 and this is path number 2. So for path 1 there are two resistors in series. So R1 is 2 plus 2, 4 ohm, and on path number 2 there are two resistors in series, 2 plus 2, 4 ohm, and then two paths are in parallel. So 1 upon Rp is equal to 1 by 4 plus 1 by 4, 2 by 4, 1 by 2, and hence Rp is equal to 2 ohm. So we can say RAC is equal to 2 ohm. In numerical 19, 5 resistors each of 3 ohm are connected as shown in the figure. Calculate the resistance between the points P and Q. So if we focus on the points P and Q first, so between P and Q, if you carefully observe this circuit diagram, between P and Q, a triangle is formed, P and Q. So to find equivalent resistance between P and Q, as usual we identify number of paths. So this is path number 1 and this is path number 2. For path 1, equivalent resistance is R1, 3 plus 3, 6 ohm, and there is only one resistor on path 2, so it is already simplified. Fine. Now these two paths are in parallel, exactly parallel. 1 upon Rp is equal to 1 upon 6 plus 1 upon 3. 1 plus 2 by 6, 3 by 6. So 1 upon Rp is equal to 1 by 2, and hence Rp is equal to 2 ohm. So now to find equivalent resistance between X and Y, first once again let us analyze the circuit diagram. So point X to point P, there is a resistor. How much? 3 ohm. Now between P and Q, we found out equivalent resistance between P and Q in sub question A, that is 2 ohm. And then between Q and Y, there is a resistor of value 3 ohm. So now as you can see that between X and Y, there are three resistors in series. So Rxy is equal to 3 plus 2 plus 3, that is 8 ohm. So total equivalent resistance of this entire circuit diagram is 8 ohm. Two resistors of 2 ohm and 3 ohm are connected in series and in parallel with a battery of 6 volt and negligible internal resistance. For each case, draw a circuit diagram. Okay, so let us draw a circuit diagram first when they are connected in series, and the series connection is connected to the battery of 6 volt, 6 volt battery. And for parallel connection, this is the circuit diagram. 2 ohm and 3 ohm in parallel, and that is in connection with 6 volt battery. For each case, draw the circuit diagram and calculate the current through the battery. So first of all, in each case, we'll have to find out what is total external resistance. That is R here is 2 plus 3 because they are connected in series, 5 ohm. Then E is equal to I into R plus small r, but small r value is 0. So EMF is 6. Current we want to find out. R is 5. So I is equal to 6 upon 5, 1.2 ampere. And for parallel connection, here 2 ohm and 3 ohm are connected in parallel, right? So first we find out the equivalent resistance. That is Rp is equal to R1 into R2 upon R1 plus R2. 6 upon 5, 1.2 ohm. Once again, E is equal to I into R plus small r value is 0, EMF is 6, current we want to find out, and external resistance is 1.2. So current becomes 6 upon 1.2, and that is 5 ampere. 5 ampere. So when two resistors are connected in series with a 6 volt battery, okay, when two resistors are connected in series with each other and then it is connected to the battery, the current is 1.2 ampere. But when the same resistors are connected in parallel with each other and then the battery is attached to that combination, the current of the circuit becomes 5 ampere. So this is a very good example to demonstrate that when resistors are connected in series, the total resistance or equivalent resistance of the circuit increases, and as a result of that, current decreases. Whereas if the resistors are connected in parallel, the equivalent resistance of the circuit becomes less, it decreases, and as a result of that, the current increases.
Thank you for watching. Please check the link in the description below for more numerical videos. Please like, share and subscribe to my channel.